Hi everyone and welcome to this lecture. Today we are going to talk about the second part of our course, that is differential equations. And let me just write it down. So the first thing it comes to mind is that what is a differential equation. So let us start with a very basic definition. The definition is a differential equation is an equation that involves the derivative of a function or functions. So you can write this definition as it's an equation that involves derivatives a function or functions. So let's see an example. What do I mean by it? Let's say you want to write Newton's law. So the most common way and the most generalized way to write is the force is the rate of change of the momentum of an object, right? But what if you have a spring mass system like this? The spring constant is k, and you know that this is written as F is equals to minus kx, that is the restoring force, and F is dp dt, that is the rate of change of momentum. And since our mass over here is constant, we can write it as ma plus kx equals to 0, where a is just the second derivative of x with respect to time. That means the acceleration. So if you just write it in an organized manner, this will look like this. So this is a differential equation. The reason is it's involving derivatives of x, because here x is a function of time, right? And that's why since they are involving the derivatives of x, this is called a differential equation. And this is the very basic definition of a differential equation. In fact, this is called a second order differential equation. A more generalized version would be something like this. And note that I'm only writing the derivatives, but there might be terms like this. For example, dx dt whole squared. It can be cubed, it can be square root, and so on. And finally, at the right hand side, there might be another function of time. So this is the most general form of a differential equation. And in the coming lectures, we'll see that how we can deal with different kind of differential equations, and we will focus on only solving some linear and some non-linear equations. The non-linear equations will be very selective, that is, we'll be very careful about them, and the range that we're going to discuss about will be very narrow, not a broad range, because most of the differential equations are very notorious to solve, and in some cases there might not be an exact analytical solution. You might have to refer to numerical methods. So before we start solving differential equations, let's just learn some definitions or some prerequisites that will help us in the long run. So one of the prerequisites is that the initial and the boundary value of a differential equation. So they are called initial and boundary conditions. So let's say you have a differential equation. Let's say this is some differential equation that is given by this box, or you can have the equation we just saw earlier. Let's say this looks like this. This is a differential equation. So what is the initial condition? Initial condition means, let's say the starting value for x, that is when t equals to 0, since x is a function of t, when t equals to 0, let's say this is 1. So this is an initial condition. And the boundary conditions mean, let's say this equation gives us a solution that is x as a function of time as, let's say, sine t, and there will be some constant over here, let's call it c1, and I want to see the solution from t1 to, that is the value of t starting from 1 and it will end up on 10. So the values of x at, let's say, when t equals to 1, it's, let's say, 2, x of 1 is 2, or it might be something else depending on this constant over here. So, and when t equals to 10, let's say this is 0, it can happen. So these are our boundary conditions. That means you have a solution like this and you draw this interval from 1 to 10. The values of the function at these points, that is the end points of the interval over which this solution is defined on, or this differential equation is defined on, are called boundary conditions. And we talked about a bit in the regime of linear and non-linear equations, so it is important to know what are linear and non-linear equations. Obviously we'll try to deal with linear equations most of the time, but it's a good idea to know that which kind of equations are non-linear. So let's say you have a function y of t and it satisfies some differential equation, let's say t squared y prime, here y prime will mean the first derivative, and let's say there is y prime squared, and let's say this is y equals to 0. This is some equation, a differential equation. So this is a non-linear equation. The reason we are saying this is, first of all, it's there is this t square and there is this y prime square. So this operator will give rise to this non-linearity, that it is not a linear operator. And if you recall from our discussion on linear algebra, that if you have an operator, let's say L, and you have some, let's say, states A and B, if it satisfied LA and LB, this was the definition of linear operator. But you can check that this operator over here will not satisfy this, so it's not a linear operator. And any differential equation that involves this kind of a non-linear operator will be called non-linear. In fact, if it contains some non-linear terms, it will also be non-linear, but we won't focus much on non-linear equations. Our focus will be mostly on linear equations. So again, take the example of the harmonic oscillator. This is a linear equation. That means if you just make a plot, let's call it y, then if you call it y and you make a plot of this equation, this is a straight lines equation, right? It's a linear equation. That means if you have x over here and y over here, you can get a straight line. So this is one way to think of these linear equations, that if you just take the derivatives and plot them, you get a straight line and no curve. So that's why they're called linear equations. At this point, I'm just telling you the definitions, but since we'll be dealing with only linear equations most of the time, it won't matter much. So the final thing we want to talk about is the classification of differential equation. So by DE, I mean differential equations. So we classify them as follows: ODE, that means ordinary differential equation. I'm writing differential in terms of di double f dot and equation in terms of eqn dot. So it's a acronym, you can say that. And the other one is called the partial differential equation. So ordinary differential equation comes from a single variable function. The harmonic oscillator, like this, that you saw over earlier, is an example of ODE. That means the solution is dependent on only one variable. But what about partial differential equation? This is a famous partial differential equation called the Laplace equation. Also, if you are familiar with electromagnetism, you have already seen it. You can see that the solutions will be looking for will come in dependent on two variables, that is x and y. So this phi is actually a function of two variables, right? And these kind of equations are called partial differential equations. So the shortest way to recognize a partial differential equation and a ordinary differential equation is just to look for the solutions and see how many variables they contain. So if it's just a single variable thing, it's an ordinary differential equation. If it's multi-valued, that is the function is depending on two or more independent variables like here, then those differential equations are called partial differential equations. So from next lecture we will see how we can solve different kind of differential equations. We will start with the first order linear differential equations and gradually move into the second order, and after that we want to see some coupled differential equations, and finally we want to end our discussion on differential equations with some Sturm-Liouville problems and series solutions. So this will be it for today, and thank you.